PowerPoint covers the Newton Raphson method. The Newton Raphson method is used to find a numerical solution to f of x equals 0. So we are solving where does a graph equal 0? In other words, where does a graph go through the x-axis? We've already seen the method of iteration, which can help us to locate roots, but this is a more accurate method than iteration. As you can see in the picture, we have a red curve, and that red curve goes through the x-axis, and we are going to try and find the location of that point. First of all, on the picture you can see that I've marked a point called A. That point A is on the curve. Next we want to give that A some coordinate names. So if you look down below to the x-axis, you can see that the x-coordinate there has been called x0. The corresponding y-coordinate could be called y0, but you can work out y-coordinates by putting the x-coordinate into the function. So rather than calling it y0, we could call it f of x0. So we now have that the coordinates of A are x0 and f of x0. Next, we draw a tangent to the curve at that point. So the tangent to the curve at that point I've highlighted in yellow. Tangents are straight lines, therefore we can use the formula y minus y1 equals m bracket x minus x1. We know the point on the line, so we can put the coordinates x0 and f of x0 into the formula. And then for the gradient, rather than using the letter m, we could call the gradient f dash. F dash is a notation that we use to show that we've differentiated something. So this is the formula for that tangent, the equation of the tangent. Y minus y1 is our y coordinate, equals the gradient, which is f dash at x0, that's the gradient notation, multiplied with x minus x0. We can see in the picture that this tangent would meet the x-axis, and I've labelled the point where it meets the x-axis as x1. Now if we look at the root that we're trying to locate, we can see that x1 is closer than the x0 was. So x1 would be a better approximation to our root than x1. The coordinates at that point would be x1, 0, since point B has a y coordinate of 0. And because that point is on the yellow tangent, we are allowed to put its coordinates into the equation of the tangent. So into the equation of the tangent, which is highlighted in yellow, we're now going to put in that y is 0 and x is x1. So you can see here we've changed the y to 0 and the x into x1. We're allowed to put that point into this equation because that point does lie on that tangent line. This equation could then be simplified and rearranged slightly. If we rearrange by taking the f dash of x0 over to the left hand side, we can get the x1 minus x0 on its own. x1 minus x0 would equal minus f of x0 divided by f dash of x0. And from there we could get x1 on its own by taking the x0 over to the other side. So we end up then with this formula, which is known as the Newton Raphson formula. To work out x1, you need to know x0, you need to know f of x0 and f dash of x0. Once you've got your x0 and your x1, you could then use that formula over and over again, as you would with an iterative formula, to generate x2 or x3 or x4, and gradually you would get closer and closer to the actual root. In general, you can see that xn plus 1 is xn minus f of xn divided by f dash of xn. This is our Newton Raphson formula. This formula is given to you in the formula booklet, so you don't need to memorize it, but you do need to know how to use it. The choice of the x0, the initial x value, is very, very important. If you choose the x0 correctly, then you will gradually get closer and closer to the real root using this formula. If you make a bad choice of x0, then you could diverge away from the root that you're trying to find. So now that we have our Newton Raphson formula, we can apply it to some examples. In this one, we're asked to use the Newton Raphson method to find a root of this cubic equation. We could first of all try to locate roughly where a root is by substituting numbers into that cubic. For example, f of 1 gives a negative answer, f of 2 gives a positive answer, so therefore it's safe to say that there's a root between 1 and 2. If we know that there's a root between 1 and 2, then 1.5 would be a really sensible place to start your guesswork. So let's say that x0 is 1.5. In order to use the formula, we need to know the function and its differential. So if we differentiate x cubed minus x minus 1, we get that f dash of x is 3x squared minus 1. So putting the function and its differential into the Newton Raphson formula, we end up with this. Now we can start to substitute our numbers in. If we put in x0 into the right hand side, so where the xn is, if we put that as x0, which remember we said was going to be 1.5, and substitute 1.5s into that formula, it gives an answer of 1.34783. Make sure that you can arrive at that same answer on your calculator. Next, we would substitute that number into the formula, and this time we would get 1.32520. Then we could substitute that number into the formula. This time we get 1.32472. We could keep doing this and get closer and closer to the actual answer. If you were asked to find the answer to 3 decimal places, you would need to keep repeating the process until you've noticed that the answer to 3 decimal places keeps coming out the same, and for this one that would be at 1.325. So to 3 decimal places, our root is 1.325. I mentioned earlier how important it was that your initial guess, that x0, is a good choice. If you make a bad choice for your x0, then the Newton Raphson method might fail completely, or it might take a very long time to converge to the actual root. As we can see in this picture, we're trying to find where the curve meets the x-axis, known as a root. So let's say we're trying to find the root where the red dot is. If we pick our x0 value here, you can see that the point is very close to the minimum on the graph, that turning point. At turning points, tangents are flat. If the tangent was completely flat, as you can see in the picture at the bottom right, then the Newton Raphson method would fail completely. That tangent would never meet the x-axis. But if we go a little bit to the right of the turning point and we draw that tangent, it does meet the x-axis, but it meets the x-axis a long way away from the root that we're trying to find. And the flatter the tangent, the further away from our root does the tangent go through that x-axis. So we need to be careful that when we choose our x0, that it's not close to or on a turning point.